So far in our conversation on Eulerian paths, we began in Königsberg, where Euler said that if we start somewhere in Königsberg and we want to traverse each of the bridges of Königsberg once and only once and end up back where we started, that it's impossible to do. And that didn't depend on how we did it. No matter what, it's impossible to do. So that led to the definition of an Eulerian path, which is a sequence of edges taken in order such that each edge appears exactly once. Okay, and this is the graph that we use to represent Königsberg. And the proposition that Euler proved is that if we have an Eulerian path, then the degree of every vertex must be even. Because we count degrees in this graph, here at degree 3, because there are 1, 2, 3 edges coming from this vertex, since this doesn't have the property that every vertex has even degree, we know there cannot be an Eulerian path in Königsberg. But we can actually say more. We can say not only when there isn't a path, but when there is. So for that, we have the following theorem, which says that given a connected graph, so what does it mean to be connected? That means between any pair of vertices, there is a path between them. It doesn't matter which path, but there is some path between them. That's what it means to be connected. So suppose you have a connected graph, then G has an Eulerian path if and only if all vertices have even degree. So let's see how we could prove something like this. So there are two things to prove. That's the first thing that you should notice. Whenever you have an if and only if statement, there are actually two statements here. There is the only if. And this is, in this particular case, so that would say that G has an Eulerian path only if all vertices have even degree. That's exactly the statement of this proposition. So this is by the proposition. So what's left to prove is the if statement. The if statement is that G has an Eulerian path if all vertices have even degree. So let's assume that the degree of V is even for every vertex. And here we have an example of every vertex in this graph you can check has even degree. It's either degree 2 or degree 4. So what I'm going to do is give a constructive proof of this theorem. And that's really the kind of proof that we want. A lot of the proofs that we're going to see in graph theory aren't going to be constructive. They're going to be existence proofs. But this one we can actually do constructively. So what I'm going to do is start with any vertex, say V0. Okay, so let's maybe let this guy be V0. Pick any one that you want, V0. Okay, and then take a walk. Take a walk and don't stop until there are no edges left. Edges left to take. Okay, so remember a walk means Indiana Jones style. Once you take an edge, you can't take that edge again. So I could take, for example, this edge first. So maybe I'll number my edges, and I can't take a numbered edge again, right? And now maybe I'll take this edge, and maybe we'll put a little arrow just so we don't forget which way we're going. And now maybe I'll go over here. That'll be edge 3, and maybe I'll go back over here, edge 4. It's fine to revisit a vertex, which I've just done. I don't want to revisit an edge, though. So maybe I'll take this one, 5. And now I'm going to walk down here, 6. And now I'll walk up here, 7. And now you can see here, I don't have any choices left. Once I'm here at this vertex again, after I've crossed this edge, now I've crossed all 3 of these edges, so I have only one edge I can take. But I do have an edge I can take. Why? That's something to think about. So I'm going to keep going, and I'm going to take vertex 8, and you know what? I'm just going to go ahead and jump back up and let this be edge number 9, and now I'm back at V. And now if we look at the path that I've taken, here I go 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm stuck back here and there's no other edge that I can take. So let's write that down. There's an interesting thing that happens. Claim you're going to end at V0. End where I began. Why? This is because every vertex has even degree. So think about what happens as I'm starting here and I leave. So now V0, I've taken one edge. And I've taken one edge from this new vertex I'm at. But when I leave it, that's my second edge. So there's always going to be, after I've visited a vertex, except for V naught, once I've visited a vertex, there's always an even number of edges left, which means that I can come in and go out. Come in and go out. So that means that I'll definitely end. So I'm going to end up with a closed, so we end up with a closed walk, and let's give it a name. Let's call it C naught. So that's a closed walk. Now it could be that I traversed every edge. So if C naught uses every edge, let's write uses a little more correctly, uses every edge, then we're done. We've actually constructed an Eulerian path. That's really what an Eulerian path is, right? It's a closed walk that uses every edge, right? Because the walk tells me that do it once. Okay, so I could have gotten lucky and I could have ended, but as you can see in this example that I just did, I didn't actually get everything. So what do I do in that case? Otherwise, choose any vertex V1 with an adjacent edge, with an edge E that is not in C naught, but connects to a vertex on C naught. So let me go through and let me highlight my vertices that get touched. So is this, oh, that works. Okay, this guy, this guy, this guy, this guy. These guys are all touched by my path. So when I think about my path C naught here, it touches all of those highlighted vertices, and it doesn't touch the ones that aren't highlighted. So I claim, here's my next claim, I can always find V1 and E with this property, with these properties. What do I mean by these properties? I mean the one that I've written down here. The property is that it's not on my graph, so it's not highlighted. Sorry, the vertex can be highlighted. It doesn't matter if it is, but there's an edge, say E, we'll take this edge, and a vertex, say V1, that touches a highlighted vertex. That's all that I need, okay? Touch a highlighted vertex. And now what do I do from there? Well, now I know that if I think about my graph with all of the edges in C naught removed, so E minus C naught, this graph still has every vertex with even degree. Why? Because an even number minus an even number is an even number. And I've taken an even number of vertices out for every vertex in C naught. Okay, so what I'm left with, every vertex is still going to have even degree. So what does that mean? That means take a walk. Take a walk using E. So, okay, let's do that. Let's do it maybe in pink. So what I'm going to do now is I'm going to say, okay, well, let's take E as my first edge. So that's going to be, maybe I'll use, I'll call this 1. Pink looks way too much like that. So, okay, for those of us who don't see colors so well, there we go. We'll do 1. And now I'm going to take a walk again. So I could do, maybe I'll do 2 here, 3. So again, where am I going? I'm going out from that vertex. So this is the vertex V that I touch that's on C. I go out from that 1, and then I go up 2, down 3, over here will be 4. I can go over here 5, and then I'm back. Great, 6. And now I'm going to stop there. And I'm going to call this C1. Okay? This is my path C1. Now what does C1 use? Well, let's change our highlighter color to blue. C1 has used this vertex, and this vertex, and this vertex, and this vertex, and this vertex. Okay, and now have I covered everything? So C naught union C1 covers more. So it might be everything. If not, go again. So you can see I'm really building out an inductive proof. So if I take maybe light green for my last color, then I can say, okay, well, all I need to do is find some vertex that I'll call V2 that touches some vertex that's either on the red path or on the green one. So I'm going to take, this guy is going to be V2, and I'm going to take this to be my new edge. Okay, and you see that I hit that vertex V there. Maybe we'll call this one W just so I'm not redundant. Okay, so now I can take my path and I can say, okay, well, I'm going to take this as my first vertex, 1, and then I'm going to loop back here, 2. And now I've actually covered everything. So this is C3. So if I take the union of those, and what I do for my path is I start on the red path until I hit V. And so I stop right before the last. So I go 1, 2, 3, 4, 5, 6, 7, 8. Switch to blue. 1, 2, switch to purple. 1, 2, back to blue. 3, 4, 5, 6, finish on red. 7. That is my Eulerian path. So I just tack all of these guys together and I get an Eulerian path. The great thing about this algorithm is you don't get stuck. Whatever you do, if you didn't finish it off, just go back and add more to it. So it's a nice algorithm where you don't have to back up. And we're going to be looking at a lot more algorithms on graphs. Some are going to be more efficient than others. This is a really nice one. So now we know exactly when we can have an Eulerian path. We have an if and only if condition. We can't do Königsberg, but we can do this graph.